All right, recording's active. Welcome back. So today we're going to discuss multidimensional latent variable models and how we estimate them with Bayesian methods. One thing I will also note is there is a new assignment, new homework. I know you just completed the homework. I'm sorry, I'll give you another one. It's coming. This is not a likelihood function. So this is running more analyses. And here, did I? Oh boy, hold on a second here. Yeah, this is correct. I just realized that this is me being ridiculous. I know, isn't it great that when you look for typos before you post something, you can't find them, but then when you actually see it posted and you're in front of a class full of people, you find all the typos. Have you ever had that happen before? That happens to me all the time. Should be a multi-dimensional analysis. All right, so the homework is effectively to go back to your personalized data set that you have, take the mathematics standards only, estimate the model that has the Q matrix that's implied by each standard being a latent variable. Right? I believe all of you have 4 math standards, if I'm not mistaken. Some of you have to aggregate up to a domain or combine a few standards to make that happen. But basically, we're going to be exploring how many dimensions are in your data. And you'll be estimating it with a Q matrix that's based on the standards I just mentioned, and then using what I would call exploratory techniques. These are just identified confirmatory models, but using lower echelon Q matrices for those, right? And doing model comparisons. And basically, if there are 4 dimensions for problem 1, I'm going to ask you to do 1 through 5 dimensions in problem 2. So there's 6 models altogether. Then I'm going to ask you to do some old school things like a principal component analysis. And I thought about long and hard about putting this in there, but I'm going to bring this back for next week's class about what we're doing with principal component analyses and so forth. But this principal components analysis is very straightforward. It's using a correlation matrix or using the eigenfunction. So you should be able to work that through. This homework is all using, with the exception of these questions, question 5 and question 6, I'm asking you to use the MIRT package and the Metropolis-Hastings-Robbins-Monroe algorithm to estimate this. The reason for that is these multidimensional models, like with 5 dimensions, or 4, which is really what you'll be estimating as a confirmatory sense, might take quite some time. So be prepared for that to happen. As a catch to that, I'm still giving you a 10% extra credit if you use Argon. So if things are taking a long time from you and clogging up a personal computer and keeping you from doing other things or slowing everything down, go over to Argon. Argon will be what to use. Okay? And then you get 10% extra for it. Okay. This is due in 2 weeks. But just in terms of the scaffolding and turning, not just scaffolding, just the instructional plan. So I'm covering Bayesian estimation today. It's difficult. Most of you were in the Bayes class last year, and by the end of the semester, I could tell your eyes were starting to gloss over with the nuances for it. So we're going to jump into the end of last semester. For those of you who weren't in the class last year, I have some links for how to catch up. So some of this may be kind of advanced, you may not have the full background for, but I'm not going to quiz you on the things that you don't have the background for yet. Okay? But next week is what to do when multidimensionality is not wanted. Okay? So the first the situation with that is think of yourself as being in a large-scale testing program that gives out unit dimensional scores. Like you've seen a lot of places, right? They have a 2 or a 3 PL, heck, a Roche model, giving out unit dimensional scores. You don't want to have multidimensionality in that case, right? We're going to investigate why we don't want multidimensionality, how we can check for multidimensionality, and then what do we do about it next time. But think of it this way. If you had these data, your personal data set, if we were using that as we would in a normal K-12 setting, like an interim assessment, these are sort of what we call interim assessments through the school year, those math standards in the Q matrix would just be lumped into one dimension altogether. And so we're looking at it from multiple dimensions. We're going to see what happens, and it's going to tie to lecture next week a lot too. That doesn't mean you can't get started. You have everything you need to do all of the analyses here, but next week will be sort of the why behind everything as well too. I promise a lot for next week, but I'm a great procrastinator. So what I promise for next week, when we get to next week, it'll be the following week, okay? I'm just kidding. Why do something today when you can put it off till tomorrow? Anyway, any questions? Any of that? All right, let's go dive in. Why would we want to use Bayesian estimation for these latent variable models? Let me ask you, why do you think that might be the case? By the way, you're also welcome to use the chat window if need be. Let's see.
I could probably go on for 2 hours about Stan with this, but it's good if you have something that's hard to estimate via maximum likelihood. If the area under the curve is intractable, if the joint distribution is intractable and hard to estimate, you can also. I like to. When I describe it, it's you get a bigger picture of what's going on as opposed to frequentist methods. So you get a visual, if you visualize it, like a visual representation of all of plausible true values, where with frequentist methods you get a point estimate with a theoretical key value attached to it. I don't know if that's the best way to describe it, but
that was a really good explanation. I really appreciate that. Yeah, let me try to summarize and take your words and turn them into mine a little bit. Bayes is great at taking really complicated models and breaking them into chunks that you can estimate through a Markov chain. So Nathan had mentioned a likelihood function. Likelihood functions are really complex. If you think about what's happening in your homework last time, you had one parameter to solve for, right? It was just the tetrachoric correlation, and that took a while to conceptualize and build. When you have a multidimensional psychometric model, now you've got numeric integration happening and all sorts of parameters, all the item parameters, and potentially structural model parameters as well too. That's really difficult. There's a lot of work going on, and if you think about what's happening in that likelihood surface, the optimizer is trying to figure out which path is the steepest descent to get to the peak of the likelihood, and each dimension of that grid it's searching, or that function, that surface it's looking over, is a parameter, right? So in some of those parameters, if there's not a lot of information, that likelihood part, if you were just to kind of zoom in on one, take a slice of it and look at that dimension by itself, that likelihood part might be kind of flat, which makes it very hard to find a peak. The Bayesian methods do two things to me that are nice. Number one, they make it so, as you mentioned, Nathan, we get a lot of feedback. We get a bunch of information about each parameter. So we get a posterior distribution. And if we're seeing a certain parameter has a hard time converging, or its posterior distribution isn't quite what we would expect it to be, that's informative to figure out where potentially our model is not working well. And then we have the second, the remedy to that is to basically increase a prior distribution, or increase the information in the prior distribution to sort of make that peak more steep to be estimated. So that's one thing. The other part that is really important, specific to multidimensional latent variable models, is that we do not have to do numeric integration to estimate the model. Right? We can use conditional estimation, meaning we sample the thetas and then we sample the item parameters, and the whole thing converges to an endpoint, a stationary distribution, we call it, given enough time, and so as long as our data meet identifiability assumptions. But what that really means is, when we talked about the algorithms last week, like EM, or marginal maximum likelihood with quasi-Newton methods, remember that numeric integral that was there across each of the dimensions, we had to use quadrature points for. And those quadrature points get quite large because every time you add a dimension, you're basically multiplying the number of quadrature points by the set for each dimension. So if you had 15 quadrature points for one dimension, it'd be 15 times 15 for two dimensions. So 125. So this exponential increase in calculations happens in maximum likelihood, but in Bayesian methods, it doesn't happen. Because every time you add a dimension, yes, you have to sample that dimension, you have to sample those thetas, but that's one step. It's one draw. There's no other integration or other things needed for it. So actually, the multidimensional measurement models are how I came to Bayesian statistics, because when I came into the world of this, the only thing we had was limited information, but I was trying to use this in a mixture model sense, and that was not at all an option. In fact, it's still not an option. So our use of Bayesian is something that you may have to encounter to get models off the ground. The other thing I'm going to mention, foreshadowing next week, and these are my words. I don't know that other people would say this the way I'm going to say it, but one of the remedies for if things are multidimensional and you don't want them to be is just hope it's not a big deal. Hope's a remedy. How do you like that? As a scientist, as a practitioner, what's your measurement program dependent upon? It's on hope. Anyway, hope that, in particular, if you have an item that measures two dimensions, that there's not a latent variable interaction between those two dimensions. There's a theorem that we're going to sort of talk about next week that describes how our unidimensional theta estimates become a composite, sort of a blend of each of the dimensions, so long as any item that has more than one dimension it measures doesn't have a latent variable interaction. Well, turns out you can estimate models with latent variable interactions. And we're going to do that, but none of the software we talked about last week will do that for you. You have to build it directly into Bayes. So this is another reason why we use Bayesian methods themselves. So we are going to test hope. Before this class, when I was reading the chapters I've assigned, actually I assigned 2 chapters for next week. I will, in a couple weeks, I'll assign chapter 7. I'm reading it, and basically, just hope. Hope there aren't no more dimensions is basically what I'm interpreting it as. Yeah, see, as long as there's no latent variable interaction, you're fine. Well, why don't you test whether it happens? So that's what we're going to try to do. Okay, so let's talk about Bayesian methods real quick. Again, most of you had taken my class last year. To do Bayesian methods, what we're going to do is use a software package named Stan. I had thought I was going to give you JAGs, but the combination of the code made it to be too lengthy for today. So I gave you a link to when I taught the class with JAGs, which was 2019. It's on my website, and you can find it there. So we'll use Stan. And what we have to, for those of you who aren't familiar with Stan, and actually I'm looking now, oh, there it is. Okay, my computer is just very slow. So our use of Stan basically is a program that will take a syntax file, something like this one right here, and convert it into C++ code, compile that code for you, and then run your model on a standalone program. So even though we're going to use R to access Stan, Stan is actually a standalone program. If you use a different package, if you use Python, if you use SAS or even Stata, there are interfaces to Stan as well that I understand exist. So you can still use Stan. But Stan itself is sort of a lengthy looking model file, has a lengthy looking model file here. But I'll try to walk through what that shows, how that works as we go through the lecture today. Any questions so far? So again, I know there's only like 2 or 3 of you who weren't in class last year, so I apologize if this is sort of a refresher for many and not quite enough for those of you who didn't take the class, but hang in there. I will work with you to understand it, sort of a high-level version of what we do. Okay, let me give you the setup again. We're going to take, remember that that first week's coding practice where we generated data or simulated data or whatever week that was, week 2. I'm taking that again. So, right, we have this 10-item, 2-dimensional Q matrix that you see on the screen here. We have 2 types of data. We have continuous data, which we'll use for confirmatory factor analysis, and we have discrete or categorical binary data that we use for IRT. Cool? Now, here's the thing, though. Those of you in my class last year saw code that looked like this, the standardized factor. Remember what a standardized factor is, or standardized latent variables. Those are latent variables that have means set to 0 and variance is set to 1. But we're estimating the correlations. So how about we start here using the CFA assumption? Does that sound okay to you? Okay. Now, in STAN, for those of you who remember last year or those of you who are new, STAN works in blocks. There's a set of what I would call very regimented prescribed blocks in the STAN syntax file. The first being the data block. These are data that STAN basically is expecting you to pass to STAN to run the analysis itself. All this is stuff I write. I literally have to name every variable. So each of these names that you see here, like n items or y or any of that came from me. The information before that variable is what we call a variable type declaration. Basically, we have to tell STAN what type of data is coming into it. And in here you'll see int for integer. Those are values that are like 0, 1, 2, 3. You might see also this little section after int that talks about the lower or upper bounds. That gives you sort of a range. On the data itself, it serves more as a check to make sure what you're passing to STAN functions the way it's supposed to, or you intend it to. But that lower and upper is what we absolutely have to impose when we create variances. If we're estimating some type of variance that has a lower bound, or some parameter that's bounded, right? Otherwise, STAN will try to estimate it from a continuum, which won't go very well. Let's see here. The data themselves that we're passing is a data matrix. Now, here it's a little bit different. Normally, we look at data matrices, and in the rows of the matrix, we have people, and in the columns, we have items. In STAN, to make this a little bit more consistent between discrete and continuous data, those two things are flipped. It's like a transpose of data matrix. So basically, each row is an item, and each column is a person. Right? So that's the one thing to think about. But now, here's the thing, when I look at STAN code, and for those of you who've worked with me with STAN, you know what I do first, right? I might get a little inclination of what data comes in, but the first place I need to go to is to describe what we're doing is in the model statement. So the model block is toward the end of the code here. This is where you specify your psychometric model itself. And here, what I try to do is figure out what the model for the observed data is, because that's where all the information I'm thinking about comes from. Okay? So here, y is my data. I'm looping across items. When I do this type of loop, it's assumed it's going across every person in the data set. So I just have to put item in the brackets afterwards. And this tilde says my observation y should follow some type of normal distribution, or it follows the distribution that's described to the right of the tilde itself. In this case, normal. So you remember in CFA what our model implied distribution was. Right? We take our model line, we have our equation for the model, y equals mu plus lambda times theta plus error. And error has a variance to it, we call a unique variance. Here, we take that and we disentangle the parts. Mu plus lambda times theta is the mean, right? What we expect y to be. We talked about that a few classes ago. And psi is our residual variance or unique variance. And we talked about that a few weeks ago too. How are we doing so far? So? Questions? Okay, I'll keep going. Number 2, you might notice here I have a set of parameters defined. I have a mu, which is my item intercept. I have a psi, which is my residual variance or unique variance. And then I have something in the middle here, theta matrix times lambda matrix. And then there's this little, looks like a tick mark afterwards, an apostrophe afterwards. What is happening here is basically this is the set of thetas that exist in our data, right? So in this case, we have 2 dimensions. We're going to pass 2 thetas in there. So each person has 2 thetas as a row vector here. And then we multiply those thetas by their respective lambdas, right here. However, the Q matrix we give is going to prescribe which lambdas should be estimated and which lambdas should not. So this is where the fun begins. Okay? What if I told you, if you take my code, you don't see Q matrix down there, but there's a Q matrix right up here. What if I told you my code should work for confirmatory models with standardized factors and any Q matrix? Would you be pleased about that? Why I mentioned that to be pleased to you about this is because if you don't do it, if you do it yourself, the trick is coding the stand code general enough to be functional for what you want it to do. You can build one stand program and have it run all sorts of stuff for you. So in this case, if you ever find yourself in a spot where you've got a confirmatory type model, CFA model in this case, and a Q matrix, passing the Q matrix to stand is all you have to do. What happens with the Q matrix is I wrote code in stand to sift through it to figure out how many loadings you have to estimate and which loadings those are. And so in this transform data block that you see right here, this transform data block runs right before the algorithm starts. So anything in the transform data block is accessible throughout the rest of the estimation process. But basically, I'm counting up how many loadings there are. All right, let's loop over across all the factors and count the number of ones in each column of the Q matrix. And then my next step is to determine which specific, if I were to envision a factor loading matrix, right? This is just a matrix where we have our estimated loadings or zeros for the ones that aren't estimated. This next block of code right here is effectively determining which items and factors, which elements of that factor loading matrix should be populated with the estimated loadings themselves. Right? So what does that mean? I'm literally looping across every item. That's the row of the Q matrix. Every factor, that's the column of the Q matrix. And if the Q matrix has a 1 in that spot, that means the item measures the factor. I note which item, I note which factor, and then I just move on to the next loading in line. How's that sit with you? Right. So now let me show you what I do with that. Right. So when I estimate the model itself, I have to define the set of parameters that exist in the model. That's right down here. Those parameters include my thetas. Those are the latent variables, item intercepts, unique variances, and then this vector of loadings. And then there's this correlation matrix. This is actually Cholesky. We'll talk about that next. But this matrix of loadings right here, this vector of loadings, is just a column vector that just has all the loadings we estimated. It's not the loading matrix. Right? So this is what I'm going to tell Stan has a prior distribution to it in the model statement. But in between there, the transform parameters block is what takes my estimated loadings from each step and spreads them into this loading matrix with a set of zeros in it as well. So basically, lambda matrix right here, I initialize to have a bunch of zeros. But then I loop through every loading, and in that previous step, the transform data, I noted the row and column position each loading should be in. What this loop is doing is just putting that estimated loading into that position. So now this lambda matrix is something that I can use a matrix product with to multiply the theta matrix. Did I lose you? For those of you from last year's Bayesian class, whatever the hell I taught last year. What do you think? Does this bring back terrible memories? It's about to get worse. All right. Questions? We're good? Just going to keep rolling on. All right. So here, back to the model statement, you'll note theta matrix, that's just my matrix of thetas, is then multiplying for each item that vector of loadings for the items. That vector itself, and with this Q matrix that has the 2 dimensions, each item will only have one loading estimated and a 0 multiplying the other theta for it. Right? So it's just taking the measurement that works, the model that works, the factors that are measuring the item. The other way around. The items that are measuring, the factors that the item measures only show up on the model line here. Okay. The rest of this code, we've got a prior distribution for our residual or unique variance. I'm just using log normal. There's a lot of debate over which priors to use. I picked a log normal because it has 2 parameters to describe its shape, but it also keeps everything positive. And one thing I will note, because psi is a variance, you'll note when I define psi in my parameters block, which is right here, this itself will have a lower bound of 0, right? And I can tell you from my own experience with my own practice that I always forget to put the lower bound of 0 there, and it breaks every time. So in running Stan, just remember the variance parameters get a lower bound of 0. That makes things not blow up. I then describe a multivariate normal prior for lambda and a multivariate normal prior for mu. Basically what this is telling us, the multivariate normal is just an easy way to make the syntax short. I define mean of lambda as almost always of a 0 prior mean, mainly because if I'm going to take a parameter that is involved in how much precision we have in theta, I want to err on the side of conservatism. I want to make sure that anything, the Bayesian prior shrinks it to 0, which makes it harder to think that we have a lot of information about theta. For mu, it doesn't matter as much. For theta is our multivariate normal density, but I need to talk a little bit about theta. So let me go over here to the slides. So here is our multivariate normal distribution. This is our multivariate normal density. This is the prior distribution of theta as well. You might be familiar in looking at this. It still looks pretty ugly though, right? Is anybody coming to appreciate this nice equation here yet? Right, this is the equation of the Taco Bell, right, in 3 dimensions. Anyway, like the bell curve shape. Jokes are flying flat today. That's all right. The problem with estimating this, and this is the interesting interplay between the theoretical psychometrics and then implementing it in a computer. You got a taste of that with your last homework, the implementing it in a computer. But there's these 2 matrix terms that are really difficult. One's the determinant, and one is the inverse. Right? In R, you can go and use the solve function. It will give you a matrix inverse. You can use the det function. It will give you a matrix determinant. But when you go to code these, if you want to make sure that you minimize the number of computational steps involved in each. And so one of the things I need to discuss is how to disentangle that. What you see prior to this turns out for each of these, both the inverse and the determinant, it's a lot easier to work with matrices that are triangular or triangular, lower triangular to build this. Because here, take a look at the determinant of the correlation matrix, or the factor covariance matrix. In this case, it's correlation. I used R for correlation because it's a standardized factor. This product itself, this matrix product, would take a lot of calculation, right? Basically, if you ever took a matrix algebra class, you may remember this, but it takes, basically you take a square and symmetric matrix and you condition on different various elements, and you make submatrices out of that and calculate determinants. So it's basically this really iterative and very difficult process. However, it turns out if you are using a diagonal matrix, a triangular matrix, a lower triangular matrix. Remember what a lower triangle is? It's a matrix that has data in the triangle and below it. And then the upper part is a bunch of zeros. It turns out this determinant becomes a product of the diagonal if you have a triangular matrix. Actually, it's the square of the product of the diagonal, but it's a lot fewer computations. So what we end up doing, oftentimes, in using the multivariate normal density, is that we don't use the full covariance or correlation matrix. We use the Cholesky decomposition of it. Remember the Cholesky? I know the Cholesky from my model code. Remember when I created simulated data down... dang it, where did it go? Computer's having a problem here. I generated a bunch of independent thetas and then multiplied it by the upper triangle of the Cholesky, or in this case, the lower triangle of itself. Basically, we used Cholesky before to take a diagonal or a triangular version of the correlation matrix. Well, here we're using it again in computation. This Cholesky trick shows up all over the place in a lot of computation because it takes something that's usually very difficult or takes a lot of steps and cuts the steps down. Why that's important is, remember, in every computation step that you have in a computer, there's floating point imprecision. There's rounding error, if you want to call it very roughly, rounding error. And the more steps that you take, the more that error may accumulate, and imprecision in your analysis comes through. So this is a method to create what we call numerically stable estimates. So, any questions on that so far? How many of you like Cholesky, the word? By the way, I've heard it called Cholesky or Kolesky, and every time I talk to somebody, they say it the opposite of what I'm on that time. So, anyway. So you don't have to show the Cholesky. I see a lot of people, when I see your cameras on, I see a lot of people touching their face. That's I'm not a therapist. That means you're giving yourself a hug. Cholesky makes you want to hug. I get it. All right? That's fine. It's okay. Just know it this way. We're not going to derive how the Cholesky works. We're just going to take it for granted that it works, okay? So we're just taking a square symmetric matrix and turning it into a triangle. That's all. And remember, the lower triangle times the upper triangle of the Cholesky results in the previous matrix itself. All right, so that's determinant. It turns out the same thing happens in the exponent. This line, I don't know if you can, hopefully you can see my mouse cursor moving around. This is in the exponent of the normal the multivariate normal PDF. Right? And that, in the exponents right here, we want to take the inverse of that correlation matrix. Well, it turns out the matrix inverses are also a lot less computationally complex if you have triangular matrices. So if we replaced R with its lower triangle times its upper triangle, right, or lower times lower transposed, and we do a little bit of matrix algebra, turns out this middle equation right here can be split, where one side is theta minus mu transpose times L transpose, and the other side is theta minus mu times L to the negative 1, right? Well, it turns out if we took one of those sides and used a process called back substitution. Do you remember in algebra, a system of equations, right? X plus y equals 1, x minus y equals 0, something like that. You have two equations, two unknowns. Remember that? If I told you x plus y equals 1, and I told you x equals 0, that would be a very simple system. What would be y in that case? It's a quiz, see if anybody's paying attention.
1.
1, that's right. Thanks for paying attention. I appreciate it. At least one of you. Actually, I can see the cameras of those who other you. I think you're paying attention. I'll take your word for it. Thanks for answering my question. But why is that simple? Nathan, why was that something you could do in your head?
Because you were given X.
You didn't have to do anything with X. You didn't have to go and translate it or otherwise solve for it. Turns out back substitution works roughly like that, right? When you have a triangle with a triangular matrix, right? That one part of the triangle, the upper top left part, has one value and a bunch of zeros. That's like X equals something, right? And the line below it has that value and a second value. Well, that first one can then be substituted into the second. And then the second one can go into the third, and on and on and on and on. But basically, the amount of computations it takes to do that back substitution, or on the opposite side, forward substitution, is greatly reduced. So we use Cholesky's for covariance matrices in almost all parts of estimation that we do. If you're in linear model estimation, like least squares estimation, we don't use a Cholesky, we often use a QR decomposition. But that also results in a triangular matrix as well. There's a little bit of a difference between QR and Cholesky, and it's not that big of a deal to think about. We could have used a Cholesky in most cases for the linear models. But this point I'm trying to make to you is it doesn't take you very long when you start building your own code to run into times where you're going to need to see the Cholesky. So let me go back to our Stan code and show it here. So one of the nice things about Stan, one of the best things about Stan, is that you can define a correlation matrix as being a Cholesky factorization. And it just needs the number of factors. So what Stan is going to build is this theta core L as a correlation matrix that's just lower triangle of it, right? And then, as a prior, circa 2009 and shortly thereafter, there is a prior distribution that we can use for a correlation matrix that's called the LKJ prior. This is the LKJ are the initials of the authors, the last one being Joe. By the way, Joe was involved in limited information model fit. Madeu Olivares and Joe was one of the papers I didn't assign to you, but one of the very first papers looking at limited information model fit. So this is all related, a lot of related science coming out here. But LKJ, this prior, is fantastic. It allows you to basically, through a single parameter, eta, specify a prior on the entire correlation matrix itself. And how it works is actually putting a prior on the components of the Cholesky decomposition itself, those values. And so here's what to know about this. I'm not going to go deep into the math behind it, surprisingly, I know. But basically, if you set this prior parameter to be 1, it gives you a uniform prior over correlation matrices, right? If you put it bigger than 1, it moves the correlations towards 0, and if you put it between 0 and 1, it moves the correlations away from 0. I tend to use prior just of 1 just because I like the uniform prior, and correlations tend to not be a problem. We just need a way to estimate them. But this is one of the reasons why I like Stan over JAGS. JAGS does not have the LKJ prior. I think in theory you might be able to build it into JAGS through your own work. However, you'd have to get to the technical part of it, number one. I know that you can do that, given your homework last time. I know that you're capable, but that takes a long time. But number two, if you're in JAGS and don't have a correlation, it's really difficult to estimate anything with a standardized factor in it, right? It's almost always marker items that you're going to have to use. So Stan's a bit more flexible. Questions? How we doing?
Jonathan, can you, because I know that part of the LKJ prior was the determinant. Can you, what is the determinant of a matrix, and how is that used in estimation? Is that something that can be discussed?
I can try. I can try. I don't have the slides for it, and my computer is, for whatever reason, going really slow. So I'm not sure I can pull up a lot of the help with this. But let me take a look at this. If you look at a correlation matrix, first of all, the determinant is in the case of correlation and covariance, I mentioned in the beginning of class the idea of if you have a vector of data, if that sort of is like a line that emanates from some origin off into n dimensions, right? Well, if you have more than one vector of data, so in this case, let's say we have a vector that's theta 1 and a vector that's theta 2, then those two lines are off into n dimensions each, but they form what we would call a hypercube. I don't know if that makes any sense to you, but it's like this, it's sort of this cube in these n dimensions. We can't really visualize it, but it's a cube out there that has some space in it. The determinant describes the area of that hypercube, right? And sometimes if you're in a multivariate statistics class, you may learn the determinant is something that we call the generalized variance in a multivariate model, right? So in this case, it's sort of like saying, what is the area underneath that whole cube itself? So I hope that helps answer your question about determinant, Nathan.
Yeah, I think so. Thank you.
It's a really interesting and complex topic. I think determinants are lovely, but the other thing that the determinant in the multivariate normal does is that area is what is part of it's what we call a normalizing constant, right? The part of the kernel of the PDF that does the work is this in the exponent. But to make the distribution integrate to 1 across every dimension, we need to put a constant that's in that part in the front, both the negative 2 pi or 2 pi raised to the negative number of dimensions over 2, and the determinant raised to the negative 1/2 power. Those are normalizing constants that basically make the integration go to 1. All right. Other questions? Vladimir.
Yeah, I have two. So first, in the code for stan, you have some parameters, but you don't have the hyperparameters for those things as part of the code. For example, in line 77, you have lambda, you have mean lambda and cop lambda, but you are not defining those things. Is that coming?
Yeah, I built this code so that, you're right, good question. The parameters of the model are on the left-hand side of the tilde, as you mentioned. This depends on mean lambda and cov lambda. Those are what we call hyperparameters, as you mentioned. But I have that so that those are input as data themselves. So when you go and send your data to Stan, you have to tell it what the hyperparameters will be. And I did it that way so that if I did, the alternative to that is to hard code, like to basically say, it means 0 for every lambda and the variance is 1. But if you hard code it, that means, and all of a sudden you want to go and change the hyperparameters because let's say the estimation doesn't go well, you have to go and change that hard coding, recompile the program, and then get it to run again. Whereas if you do it this way, where you input it as data, you can change it with a different data set.
Okay, and you will show us that part of the code later.
Hopefully, yes.
Okay, great. Gotcha. The second thing is, can you go back to the slides, please?
Yes.
I have, and let me see mine here. Because when you compare Stan and Jax, for Stan you said can directly model continuous parameters only and
Yes.
not discrete parameters. What's the meaning of that? Because I thought that regardless of the parameters we use for Bayesian analysis, those would be continuous. What is an example of a discrete parameter?
Well, in 2 weeks we're going to talk about mixture models. A mixture model is basically a latent class a person gets assigned to, and that class itself is a discrete number, a discrete value. All right, so you might be in class 1 or class 2. Those are themselves discrete, and the reason why Stan will not model that is the type of Monte Carlo it uses is called Hamiltonian Monte Carlo. It basically is suggesting really efficient parameter draws, but it's doing so based on Hamiltonian physics, so some concepts of Hamiltonian physics that are beyond me in some cases, but part of it is they need a derivative of that density of the parameter itself. When you have a discrete parameter, the density is a step function, so the derivative is undefined, so it's not able to actually do that. Now, does that make sense? Did that answer your question, Vladimir?
Yes, one follow-up question is, so for the case of discrete parameters, we are talking about latent variables, not the dependent or predictor variables we can use.
Correct. Anything that
Okay.
you need to go. The other place where this would matter would be if you have a discrete observed data, but you have missing data and you want to impute that missing data. Stan will not let you do that because each of those imputed values is like a discrete parameter.
Okay, great. Thank you, Jonathan.
Nathan has a nice link. Thank you, Vladimir, for the question. Link in the chat. The other thing I will also mention is, maybe Nathan, this is a challenge to you, or I'm throwing the challenge out there. I just was in the rabbit hole of Stan for a different project I'm working on. Basically, I wanted to resample in Stan from a vector. And because I basically wanted to take a vector and draw at random a value from it, I wanted to get an index, right? If I had 10 observations in the vector, I could just imagine drawing, with probability 0.1, drawing any one of those parameters. Problem with that, though, is that Stan won't let me. But it turns out, Stan, if you really want to get into the nitty-gritty of it, you can actually code your own things in C++ and link it to Stan. And I think this might be a backdoor way to turn Stan into making it work with discrete parameters as well. But I didn't have the time to go dive headlong in there. But if anybody's interested, or I'm going to put the challenge out there, go look up linking C++, auxiliary C++ code to Stan. It seems it's going to take a lot. You got to learn a lot of C++ to make that happen. All right. Give me just 1 second here. The sun has come out, which makes me in the position of my desk blinded by it. So let me do that. There we go. Okay, other questions? All right, let's go back to the code real quick. Here, so once again, what we specify is the correlation matrix using an LKJ prior distribution, and I import the hyperparameter as a piece of data as well too. And then to do the multivariate normal, Stan has a built-in function that just takes the Cholesky of the correlation matrix as its covariance term. So it's built around the Cholesky factorization already. So that's that. A couple other things in rapid fire succession. I know this is going to go quick. The Cholesky of the correlation matrix is, to me, uninterpretable, right? The numbers, the values in it in the lower triangle are combinations of all the correlations there are plus the diagonal of ones. So to output the actual correlation matrix, we use the generated quantities block. This is a block of terms that basically creates new statistics every step of the chain, and we just multiply the correlation by itself, by its transpose of itself. There's a function, multiply lower tri by itself transpose. Sounds like I'd name it. It's like a 30-letter name. But that gives us the correlation in the output. All right, final part of the code. And again, I really don't have the time to go deep into this, but this last part of the Stan code is for two types of model fit. Absolute fit with using posterior predictive model checks. So how well does my model fit the data? And then relative fit using either leave one out or widely available or Watanabe Ake information criterion, WAIC. The latter part, you will note here, uses a likelihood function. So basically the likelihood of the data based on your measurement model itself. You calculate a person likelihood of all the items every step of the chain. That's how it functions. The SIM-Y, the posterior predictive model checks, is a really interesting way of looking at data. Basically, every step of the chain, we pretend all of the values of the parameter are true, and we generate a data set as if they were true. And then when we're all done, we take summaries of that generated data set and come up with distributions. We call those the predictive distributions. So for instance, we could look at the correlations, right? We know the target distribution in CFA should have a correlation matrix, right? We can go and look at our correlation or covariance matrix. We look at each of our model implied covariances and compare that with what we've seen in our data. But again, this is a woefully short introduction to Bayes and what we do. but I think gives you the picture. So this is the model for CFA. You can run this, again, this is a confirmatory model with standardized factors. I have another model that uses marker loading. So this is where we estimate the full covariance matrix, not the correlation. But remember, to estimate the factor factor variances, we have to set one loading equal to 0 for each dimension. This is what happens here. It basically takes the very first loading on that dimension and does so, and the code that I built for it will automate the process for you. So if you want to use a model that has standardized factors, you grab this stdfactor.stand file. If you want to use a model that does marker items for the loadings, for the variances, use this file. One other file, though, and where you see this in your homework, and we've done this in estimation in other classes as well, the lower echelon Q matrix. Remember that? Why do we use a lower echelon Q matrix sometimes? Everybody want to answer? Pop quiz.
To conduct exploratory analysis?
That's right. It's our exploratory factor analysis using a confirmatory method. But to use a lower echelon Q matrix, we have to have no correlations in our factors, or independent standardized factors. So that's where you see this file, CFA lower echelon. It will basically estimate theta using a standard normal distribution. So means of 0, variances of 1, and uncorrelated. But this will implement it as well. So we have 3 different models for CFA. Turns out those 3 different models appear in IRT as well. The only difference in IRT is that our data are now defined as integers. I'm only using binary items, right? So they're integer valued. And then the distribution for the items is no longer normal, it's Bernoulli. And Stan has this function called Bernoulli logit that basically takes the inverse logit, or e to the term I just highlighted, over 1 plus e to that term, and puts it into a Bernoulli distribution. That's the main difference between the two. Part of that difference, though, is that there is no unique variance or no psi parameters in the IRT models. So that's been removed altogether. But everything else is the same. All right, so trying to underscore that fact that CFA and IRT, basically what we call CFA is putting a normal in this spot, and what we call IRT is putting a Bernoulli in that spot, right, for the likelihood. But again, you will also find an IRT model with marker items here as well, and you'll find the lower echelon form as well too. So 6 models altogether, right? The standardized factor confirmatory Q matrix, the marker item confirmatory Q matrix, and the independent factor lower echelon Q matrix. But those 3, you can do pretty much all the analyses in the homework. I'm not asking you to do this with homework, though, but you could use these for homework if you wanted to as well. Likelihood ratio tests don't exist here, though. Questions? Questions on any of this so far before I get to how we use it? No questions. All right. Let's go put this into practice here. In the Stan 08 Stan file here, what you will note is that we have at the beginning of the file a bunch of creating the data. So this is all simulated data. But the part that we need to talk about the most is what we do with the Stan file itself. So this very first CFA factor core marker loading Stan object here, we have to take that syntax and build a Stan executable, or basically a program that stands alone. So Stan will translate that syntax to C++ and then compile it into its own model. That's what CMD Stan model does. It compiles it. And in fact, this is probably unadvised, but I'm going to do it anyway because I like to live on the edge. I don't gamble in real life, I just gamble when it comes to class presentations. And let's see if this one bothers me here. But if I run all this code above this, right here, what you will see when it gets to the last part of the code. Oh, no, it didn't. Where is it? Is it going to? Nope. There it goes. This is what is happening. It's compiling the stand program. You see at the bottom of my screen, it says compiling. That is it translating stand to C++, and then taking that C++ and compiling it into an executable. That executable will run standalone on my computer. If I wanted to give it data, it would work. But that's the process. And then it gives you all this other output of the compiling process, which is annoying to look at. Gives you warnings, but it's not up to you. That's Stan's writing of it. But so it takes a little bit of time to compile the program. But that is what happens. Let me see if I can do this here. No, that's not what I wanted. Get back. There it goes. All right. But then what do? Well, we have to load up all of our data. So first, what you'll find in this file, which we're going to run out of time today, but I would encourage you to go run this on your own computer, are 5 models for CFA and 5 models for IRT. Let me tell you those 5 models. The first is an exploratory CFA model with a lower echelon Q matrix in 3 dimensions. Right? So we know the data have 2 dimensions. We're going to try a 3-dimensional model to see what happens. And then we're going to try a 2-dimensional exploratory model to see what happens. Then we're going to try a 2-dimensional model with, pardon me, did I say 5? Yeah. Then we're going to try 2-dimensional model with the correct Q matrix. By the way, the 2 exploratory models use the lower echelon stand code. The correct Q matrix uses the standardized factor stand code. And then we're going to do that same correct model, but with marker loadings, just to show you how the stand code works. And then finally, a 1-factor model. So you can think about what we've just done here. That those 5 models, turns out every model is nested within the 3-factor model as you go through. So this actually gives us a model comparison as well. But here is what happens to build the model. After you've compiled your stand code, the next thing is to create an R list that contains the data. So what I do to figure out what's in my data is I start with my stand file. In this case, I'm doing the lower echelon stand file. I go up to the data part, the data block, and I note all the names of the variables in that block. I then go back to my R code and I make sure the R code has those same variables in my list, and obs, and items, and so forth. Right? So I have to match each variable in the data block to build my R list. Now, to run the model itself, I take the object that was created when I compiled Stan. This is called an R6 object, and if you're not familiar with R6, don't worry about it. But basically the idea is after the $, we can put functions in R6 objects. So we're going to use the sample function. We're going to pass the data, a random number seed, the number of Markov chains we want. I'm doing 4 because they're all supposed to converge to the same point. They're going to run in parallel if I do it correctly. We'll have 2,000 iterations that'll be what's called warm-up. So basically that's running the Markov chain to try to get to a posterior distribution that's close to where the steady state of the chain is. And then after those 2,000, we take the final 2,000 as samples. So each chain, we get 2,000 estimates for every parameter. Finally, I'm including an initialization function. For those of you in Bayesian psychometric models last year, you'll remember Stan had issues, or has issues, in that it randomly starts our parameters, and sometimes it might start with theta and lambda both being positive, but it turns out if you look at the IRT or the CFA model function, lambda times theta is also equal to negative lambda times negative theta. So the likelihood it can be on either side. I don't want that to happen. So basically I'm starting all my lambdas using a random normal distribution with a mean of 5 and a standard deviation of 1. That's just the starting value, so they're all positive. And the next thing I do is I give a standardized sum score for theta. That standardized sum score basically allows me to keep theta and lambda in the right direction to make sure estimation works. Those of you who've tried really complicated models, and you know who you are, you'll know this only works sometimes, but it usually works for these models that we have in here sufficiently. So this now runs the sampling process. I'm not going to run it for you because I actually I ran it before. It does take a while to run. You can see the file itself is this CFA. Here, let me get my R screen up again. Here. Load. Hang on one second. Come on, computer. Let me show you what's in the output here real quick, and then I'll be done. Oh, get away, get away, get away. Okay. Bad restore file magic number. That might be because, let's see here. I'm in the wrong folder, that's why. Nope. No such file or directory. Give me 1 second. There it is. Nope, that's, yeah. Anyway, not going to work, so can't show you that. But I do encourage you to run the code yourself. That's all I can do. I apologize. I am running out of time today anyway, so I'm going to keep going. We'll end at right about the top of the hour, so if you're planning on the 1:50 break, it might be just a little bit late, so let me just say that. Basically, I do the same thing for the two-factor model, exploratory model. If I wanted the compare model fit, there's a function called LOO compare. Leave one out to compare. This gives you basically like information, like evaluating information criteria. The one at the top is preferred. It also gives you sort of a standard error of the of each value, which is really nice. So it tells you how much uncertainty there is in the information criteria itself. I think that's helpful. Then we get into the CFA model with standardized factors. And on and on and on. This is very repetitive. In fact, GitHub Copilot, once I did this for CFA, helped me fill it out for IRT in seconds. It was no big deal. But I'm not able to show you all of what happens. But you can see, if you do run this, I do encourage you to try running this on your own. Because at the very end here, you'll compare all the models themselves. And that will be where you'll see the model fit, how it works. Turns out, when I ran this, the Bayesian model fit did select the right model, whereas the non-Bayesian model fit tended to not select the correct model, of all things. So this is foreshadowing what we're getting into next week. But that's basically what I have for you. Questions. What questions do you have for me today?
Jonathan,
Yes.
I have a quick one. So, looking at the stan file, where the same file that you are showing us, those prior those hyperparameters you have for some parameters in the model, those things are uninformative, right?
Usually, yes. However, some start to look more informative. For instance, the loading for the lambda itself. The variance of it basically is a variance of 1. So think of a standard normal distribution for each loading with a variance of 1. That might be on the verge of informative. But that's a good question. The reason why that's there, let me give you why I did that, is that this lower echelon three-dimensional matrix is just identified. And estimation of just identified models is very difficult from a likelihood sense because that likelihood may not be very informative itself. So the only way that we can really get estimates that are stable is to put more informative priors on it. So in this case right here, in this example, I've put a prior that's more informative than I would otherwise want to do so on the loadings. Does that help answer your question?
Yes. Yes. Thank you.
Thank you. Very good question. That's the other thing I will note to you is I don't know that in any of the classes that you've ever heard me talk so much about this exploratory stuff. And you know I really hate exploratory methods from a philosophical point of view. But I'm giving this to you because I want you to be able to converse in that as well too. Basically, we can take a model here and estimate exploratory versions of the model. But remember the idea, what Stan is doing is building a likelihood function. And what I told you about exploratory, there is no such thing as exploratory, any factor analysis, IRT, whatever, with a likelihood function. You have to make a series of constraints, in this case, the constraints provided by the lower echelon Q matrix. But this is exploratory. So it's exploratory through a confirmatory method is basically what I'm building here. Other questions? Okay, let me talk about where this is going. Next week, again, you don't want multidimensionality. You have a unidimensional assessment program. What do? Well, first, we're going to have to figure out if there are multiple dimensions. We're going to use these lower echelon Q matrices to do so. Number two, if there is multidimensionality, what do you do about it? Culminating with my favorite one, just hope. Hope it doesn't matter. Hope is not a great... if you're writing a proposal for a grant, hope is not really part of the methods section. You'd probably get hurt on that pretty quickly. Not a good review. All right. Anybody else have any other questions for any of this? No. Well, then I'm going to stop.